In earth science, models are used to demonstrate complex processes and abstract ideas on a scale that students can work with and connect to. An unfortunate reality of models is that they are incomplete and are simplified to fit different learning levels. Often through the simplification of a complex idea, misconceptions and confusion occur that result in frustration for both students and teachers. Our research group has chosen a topic whose current models foster those misconceptions and confusion: the cyclical pattern of tides and tidal movement. The current model for tides is the two-bulge model. This model is incorrect, not only in its exaggeration of the change in ocean level, but also in its oversimplification of the extremes in the tidal cycle, the spring and neap tides, and the lunar and solar orientation in respect to the Earth affecting daily tidal changes observed at coastlines. This model has led to many misconceptions, such as the idea that tidal waves are the extreme catastrophic waves seen in movies, rather than the daily oscillations. This model also highlights the effect of the gravitational attraction between the Earth and Moon, while hiding the forces that drive the daily observable tidal changes. This view of the Earth-Moon system also assumes a lot of prior knowledge, including how gravitational attraction works, a deep understanding of the lunar cycle, and an ability to understand the connection between the ground observations and the relative locations of moving celestial objects. This model also suggests that high tide and low tide occur across the same longitude at the same time as the Earth rotates in respect to the Moon. Observational data proves that this is a misconception and that high and low tides vary in the same longitude. This hidden information prevents students from connecting one scale of observations to another. The forces behind observed tidal movement are much more complex than the original model suggests, and its simplicity has limited students' ability to connect the abstract thoughts to the physical world around them. Daily tidal movement that is observed by wave height measurement is driven not only by moon location, but mainly by the Coriolis effect. This can be seen in wave height data as the high and low tides move around the ocean. The water moves in a counterclockwise rotation in the northern hemisphere and a clockwise rotation in the southern hemisphere. By leaving out this important fact, students lose the opportunity to create connections to the effects of the Earth's rotation, which is also seen in weather patterns, storm movement, and ocean circulation. We feel this piece of missing information is preventing deeper understanding of this process and will create a divide between the larger forces that affect so much of the Earth science processes that our standards are based around. To better demonstrate how the Coriolis effect is a driving factor in high tide and low tide movement, we have developed a dynamic concrete model that allows for students to observe the cell's direction and movement of the high and low tides in a simulated ocean basin. This model is meant to work inside a larger unit to describe the forces that lead to the cyclical changes in tides. Our model design mimics the Atlantic Ocean basin, with North America, South America, Europe, and Africa used as a way for students to gain geographical perspective. The materials we used for this project were relatively simple, with the most expensive being a 38 cm by 32 cm rectangular aquarium. The continents we built out of a hard plastic bin that we cut into the appropriate continent shapes, which we then glued to transparency sheets that we cut and formed to fit alongside the bottom of the continent to conceal the pumps from view. We then spray painted the entire pieces black and glued on suction cups using Gorilla Glue. Underneath the continents, we cut out space for the pumps to push water out. The pumps we used were submersible water pumps that have a 90-gallon per hour capacity. We used fine glitter, blue food coloring, and styrofoam balls to allow for easier viewing of water movement. To set up this model, we filled the tank with 10 centimeters of water. Once full, we put the continents and the pumps into the tank based on previously measured markers for each of the pieces. The pumps are placed at the center of the tank on the left side underneath the connection of North and South America, and the other two pumps on the other side of the tank at the far left and far right corners. The water was then dyed blue and glitter added to the top. Once the pumps are turned on, two cells will begin to form. A small styrofoam ball can be placed into the water to better highlight the high tide movement. With this configuration, we can see two cells, one in the northern hemisphere moving counterclockwise and one in the southern hemisphere moving clockwise. This model will be part of a larger unit to help students understand cyclical patterns in earth science through inquiry-based learning. Our unit focuses on students observing cyclical patterns on 3 scales using various labs. Moving from small concrete ideas to larger and more abstract scales, students will study tidal patterns using their own observations and data collection. The first scale will focus on how tides are seen on a daily basis, which focuses on accessing students' prior knowledge and exposure to new tide and oceanography vocabulary. Student inquiry in this part will be based around a lab where students map their own diurnal and semidiurnal tidal charts from NOAA buoy data. Moving to a wider perspective, students will be noting how cyclical tidal movement can be seen across ocean basins, with our model being used as a medium for students to observe the cell movement and be able to predict why the high tide and low tide would move in this way. Finally, the end of this unit would go out to the furthest scale with connecting the tidal extremes of spring and neap tides to the location and gravitational effect of lunar and solar alignment with the Earth. We worked with the New York State Science Learning Standards along with currently used textbooks to design a unit and set of models that can be used effectively in high school classrooms. This unit is a way to address the 7th standard in the space systems portion. This unit plan introduces students to core ideas that will be used in future units, along with addressing and working with cyclical patterns using tides as a medium to observe this pattern. Using this set of models, teachers will be able to build their class's prior knowledge through a concrete model, allowing for recall and experience with observing and documenting cyclical patterns that will be useful when working with other cycles such as lunar. All models hide and highlight different aspects of real-life processes for the ease of education. In our model of the cyclical patterns of tides and tidal movement, we chose to highlight certain aspects while hiding others for practicality. Although we are trying to show that the high tide travels around the Atlantic Ocean basin in a circular motion, it appears that the circulation of the tides is flowing around the basin like the Gulf Stream, when in actuality the water is more of sloshing around the ocean basin.